On Friday, we were talking about molarity as a form of concentration. And we said molarity is an intensive property, as are all concentrations. And this means that it does not matter how much there is, that concentration is the same. So when you go into lab and you pour out a few milliliters out of the bottle of whatever, let's say it's 1 molar hydrochloric acid, that doesn't change the molarity of what's left in the bottle because you've removed some. Okay? So molarity is represented by the letter M, and it has the formula of moles of solute over liters of solution. Sometimes it is written as N over V, where N stands for moles. Why N? Because we have so many things that start with M in chemistry, and so we have to use some other letters sometimes. Most likely, you're not going to have very many practical situations where somebody tells you the moles and then you have to figure out the concentration. But once we get to the stoichiometry, this happen a couple of times. So let's say we have done some sort of lab experiment and we have figured out that we have 5.00 milliliters. We can measure that very precisely with a pipette. Pipettes are also very, very precise, much like the volumetric flasks we talked about on Friday. So you measured out 5.00 milliliters of acetic acid. Now, acetic acid is the one acid of the things that you were supposed to memorize that just has like letters all over the place because we write the structural formula. So it's CH3COOH. That tells us I have a carbon with 3 hydrogens. Next in line is a carbon attached to an oxygen and another oxygen that's attached to a hydrogen. So I have 5 milliliters of this, and I've done whatever experiment, and I figured out in this experiment, I have 0.00453 moles of, I'm going to just abbreviate this as HAC. H at the front tells me it's an acid, and AC for acetic acid. Okay, so these two things are equivalent. It just makes me not have to write as much. So first of all, I want to remind you that we can convert between milli and no prefix by using 1,000. So we want this in liters. I can just move the decimal point, right? I'm going to move it by how many places? 3. In chemistry, we're almost always moving it by 3. A milliliter is really, really small. So compared to a liter, it's going to be a tiny portion of one. So I would be moving it in this direction. 1, 2, 3. And I would have 0.00500 liters. Do I keep, and I'm going to erase that there because this was a decimal. Do I keep these zeros? So if I look back here, these are significant. They're right-hand zeros and there's a decimal. And they are right of the last non-zero, not right of the decimal point. They happen to be right of the decimal point, but they're also right of the last non-zero. That's what's significant there. All right, so in that case, we do keep those. These are not significant, but we need them there. They are important because they tell us how big the number is. Okay, so we can just divide these. The molarity then is going to be 0.00453 moles divided by 0.00500 liters. Is that going to be more than 1 mole per liter or less than 1 mole per liter? Less than, right? So I should be expecting something in the ballpark of maybe 0.8, 0.9-ish. Let's see what happens. I get 0.906. Anybody else get that? Okay. Now, if you are comfortable going between milliliters and liters, you might be interested in a different method of doing this. If not, you can ignore this portion. I'm not going to require you to do it this way, but this is something that I sometimes do. I don't like looking at numbers that small because I lose track of the zeros. So instead of converting this to another number that looks like that, I'm going to convert this one to millimoles. So 0.00453 moles is equal to 4.53 millimoles. Okay. Then I can do my molarity as 4.53 millimoles per 5.00 milliliters. I don't have really the right units for either of them, but since they're both in millis, I'd end up dividing by 1,000 in one case and multiplying by 1,000 in the other, and those two would cancel out. This is going to give me the exact same number. 6. What units do I use for molarity? I can express it two ways. So one way is moles per liter, or I can just use a capital M, either way. Okay. We are more likely, if we are in lab trying to prepare something, we are going to need to use grams into moles. Now, sometimes you might be told you need to prepare a solution that has a certain concentration. So we want a 0.200 molar solution of sodium hydroxide. If I say sodium hydroxide, you should be able to come up with this formula, Na for sodium, OH for hydroxide. That is 500 milliliters. Okay, so we are going to have a container that we can fill to at least 500 milliliters, and then we are going to have to put some sodium hydroxide in there. Do I want to put the 500 milliliters of water in first? What would happen if I put in 500 milliliters and then added the sodium hydroxide? It would be more than 500 milliliters. And this is why we use those volumetric flasks. So as a general practice, what we generally do is dissolve our solid in a smaller amount and then fill it up the rest of the way with water. Now, why would we use deionized water? What would deionized mean? That's what we use in lab. Ions, right? Yeah, there's no other ions in there. And some of the most common ions to find in water would be things like sodium, calcium, hydroxide or hydronium, which would change the pH of it. Chlorine might be in there. And so if any of those things might interfere with what we want here or what we're going to do with it, we want to make sure we're using deionized water. What mass of NaOH? You're going to say the molarity is equal to moles per volume, right? And we need to know how many moles of the NaOH we need and then convert that to mass. And so we said on Friday, we can rearrange this equation, move this volume over here. Moles is equal to molarity times volume. And then I'm going to put a little uppercase L there to remind us that that volume needs to be in liters. So 500 milliliters, what is that in liters? 0.5 liters. We know 0.5 means half, so it's half a liter, right? Okay, so we are going to need 0.200, keep my units, moles per liter times 0.500. And since I have the decimal here, that means these zeros are significant. So I'm going to keep those zeros here. Liters. 1 liter is on top of a fraction or, by itself. 1 liter is on the bottom, so I can cancel those, leaving me units of moles. All right. And so my N is going to be 0.100 moles. How do I get from moles to mass? This is where we have to get on the mole train. Anytime I'm getting on that train, I need a ticket that's telling me where I'm coming from and where I am going to. Yeah, Faith. Instead of dividing here, could you multiply? Well, this is actually multiplying, right? So what did you want to do dividing wise? Or is that your suggestion for getting to mass? Okay, yeah. So with our mass, well, first we need the molar mass, and we'll see what we're going to do with it. But I think you're going to be right. We are going to have to multiply. Okay, so normally we have divided because we were going mass to moles. We're going to go in the other direction. But we need something that has units of moles and units of mass. And that ratio or intensive property that has moles and mass is what? Molar weight. Molar weight of what? The NaOH. There's also water in there, but we don't need to add water. We need to know how much of this we're adding. So we need the molar weight of that. All right, so we're going to leave this alone for a moment. We're going to say NaOH is going to be 22.99. Now, sometimes I can just round whole numbers and be close enough, but as a general rule, just always keep two numbers after the decimal point. So 22.99, 1.01, 16.00. Okay, so this is going to give me 40.00 grams per mole. That's my ticket. It's got 2 units. And so Faith is suggesting that we multiply this rather than dividing. So what happens if we do that? We've got grams on top and moles on bottom. Now it's 40 grams for how many moles? Just 1 mole, okay? Because this is the ratio. We're not going to plug this in again. We're going to multiply this by this, okay? So this molar mass that we come up with, this intensive property, it's the same no matter how much NaOH I have. So it's always per 1 mole. All right, what happens when I do that? I cancel my moles and I get grams, so multiplying was the good thing to do. All right, so that tells me my mass, 4.00. Now I've got 4 sig figs here. I have 3 sig figs here. How many sig figs do I get in my answer? 3, smaller of the 2. So 4.00 gram. Okay, so I'm going to dissolve that in, say, 300 milliliters of water. Get it good and liquefied, no little solid specks on the bottom. And then I'm going to add enough water so that I get to 500 milliliters. In most cases, we don't need to be that precise with our concentrations, but if you do need to be that precise, that would be the proper tank. Okay, so that is how we figure out what mass we need in order to prepare a solution. All right, so coffee and tea both, the amount of caffeine can change quite a bit depending on how it's prepared. You know, how much sugar are you adding, how much milk, that's going to dilute stuff. So this is just an example. This isn't like every cup of coffee if that is what you are thinking. That just formula for caffeine is C8H10N4O2. Okay, so let's start by figuring out what we need to do here. We have a cup of coffee, we have milligrams of caffeine, we have a volume, and we want to know molarity. Molarity is going to be moles per liter. So what's something that would be helpful for me to do? Yeah, we want to have our milliliters in liters, okay? So 240 milliliters divided by 1,000 is 0.240 liters, okay? Anything else that might be helpful? Yeah, molar weight's going to be really helpful here. Okay, so we've got 12.01 times 8, 1.01 times 10, 14.01 times 4, and 16.00 times 2. Pull out your calculator, see if you can do that. Now notice I'm not multiplying each time. I'm going to add these to each other. So I need to multiply each step along the way and then add it up. I had a few people that were like multiplying everything and got really huge numbers.
194.22.
Okay, anybody else get something similar? Okay, now I got it too. So 3 people have 194 point what? 22. So this is grams per mole. All right. That was helpful. So all along the way here, even though I'm not getting to an answer, if I were doing this on a test, I'd be getting some points. You get a point for converting to liters because you knew that you had to have it in liters. You'd get some points for finding the molar mass. So even if you don't know exactly how to get to the answer, if you're starting to make some progress, I can give you some partial credit. So don't just leave things blank. Try something. And when in doubt, try and find moles. Do something with moles. Okay, so we got grams per mole. Now this has moles on the bottom. We want moles on the top. And here we have milligrams. So what's something else I might do? Yes, okay. So I could take my 195 milligrams of caffeine. And since I'm getting on the mole train, I want to divide to get to the moles. So I'm going to go 194.22 grams per 1 mole. Does that look like that's going to be effective? Yeah, these units aren't exactly going to cancel, but it's going to be in the right idea because I just have a factor of 1,000. So I'm just going to have to move that decimal. So if I plug this in and then remember, oh yeah, all I need to know is I need to know, do I multiply by 1,000 or do I divide by 1,000? So I'm going to divide by 1,000 here. So here's 1,000 milligrams times 1 gram. All right, that should get me to mole. Well, that's interesting. I'm going to work out to right about 1. I didn't even realize that when I picked 195. All right, 195. Probably going to be a good idea to keep bringing your calculator to class because the more you plug this into the calculator yourself, the easier it's going to be. All right, I got 1004016. I'm going to put the 1. How many sig figs is my answer going to have? Okay, so I have a 3 here and I have 5 here. So I'm going to have 3 here. 100. The next one's 4. So do I leave this as a 0 or do I round up to 1? Leave it as a 0. Okay, so this is moles. All right, that my final answer? No, because I want capital M. So this is going to be 0.00100 moles divided by 0.24. Oh, I didn't check my sig figs here. How many sig figs should I have? 2. So I don't need this 0. It's just going to be 0.24. And this, how many sig figs do I get in this answer? Just 2. So I'm going to call it 4-2. Anybody else get that? Yeah. So there we go. So we have found molarity from milligrams. We have found grams from molarity. Let's practice doing a dilution problem. Okay. So MCVC equals MDVD. Or sometimes you will see this as M1V1 equals M2V2. What does molarity times volume give me? If I rearrange this, the molarity times volume, what does this N stand for? Moles, right? Okay, and so what this is saying is that when I'm diluting something, the moles of what is dissolved, the caffeine or the sodium hydroxide, those moles had not changed, okay? So all I did was change the volume of the solution. So what does C stand for? What does D stand for? Diluted, yeah. So C stands for concentrated, okay? So just try and keep the same things together. On each side, you will have one number that is bigger and one number that is smaller than the other side. Because as your volume increases, your molarity is going to decrease. So let's say we were also trying to make this solution that was 0.2 molar and 500 milliliters, but we already had a solution somewhere. And so rather than starting from scratch, we're just going to use up this concentrated solution. So we need 500 milliliters of a 0.2 molar sodium hydroxide solution. We have a bottle that is 3 molar. What volume of that 3 molar solution should we use to dilute? And clearly we're going to dilute to that 500 milliliters. So the interesting thing about these dilution problems is it doesn't matter what the chemical is, because since it's already dissolved, we don't need its molar mass. We already know how many moles are there. So for dilution, the identity doesn't matter, not molar mass. Okay, so we know this happens to be sodium hydroxide, and it's going to be really tempting to say, oh, we're going to stick that 40 grams per mole in there somewhere, but we don't need it. It's already dissolved. So if we're taking something that's dissolved into something that's dissolved, we don't need to go through grams. Okay, what I like to do is label the numbers that I have when I have a lot of different numbers. So I'm going to label these. This 500 milliliters of 0.2 molar, is that dilute or is that concentrated? So let's think about this. We've got 2 concentrations, 0.2 and 3 molar. Which one is more dilute? 0.2. The higher number is more concentrated. So this is MC, and this is MD. Okay, and then that means the volume that is with this, if I've got an of between those 2 numbers, they go together, this is V. D, dilute. And I took a shortcut on Friday and forgot to tell you I was taking a shortcut. So I will do it the long way and then tell you what the shortcut, what I did on Friday was. Some of you might have been like, wait a minute, we skipped a step. We did, but it was kind of something canceling out. Okay, so if I plug these things into the formula up here, I've got MC, and that looks like ML. Let me make it a C. MC, so that's going to be 3.00 moles per liter. And then I have VC, well, that's what I'm being asked about. So that I'm just going to leave as VC. I don't know what that is yet. And then I have MD, that's over here, 0.200 mole per liter, and 500 milliliters. All right. Now, because molarity is in liters, I want to convert this to liters, and I didn't do that last time. So I'm also going to tack on here 1 liter over 1,000 milliliters. Now, this 1,000, I don't need a decimal point because it has infinite significant numbers. It is an exact number. It's like a counting number. Okay. I don't want to drop any zeros, so I'm going to plug this in. 0.2 times 0.5 divided by 1,000. Now my calculator is telling me this is 0.0001. How many sig figs should I report between these numbers? So these are the 2 measured numbers. They're the most important ones. How many sig figs do they have? 3 each. So I should report 3 here. At the moment, I'm only reporting 1 because these are important but not significant. So I'm going to tack on 2 more zeros. And then let's see. I have milliliters canceled, liters canceled, so this must be moles. And so that is equal to 3.00 moles per liter times VC. Algebra tells me the golden rule is to do unto one side as I do unto the other. So I'm going to divide both sides by 3 moles per liter. Okay, these moles are going to cancel. This liter is on the bottom of this fraction and on the bottom of this fraction. So twice on the bottom means it goes on the top. If you don't quite understand that, just trust me on it and then check with the math professor and they'll explain it. Okay, so this cancels and I've got my volume is equal to 0.000333. I feel like I did something wrong there. That's way too small. I know what I did. I divided this by 1,000 twice. I plugged in 0.5 instead of 1,000. So let's try that again. Anybody get a different number than this here? Yeah. Okay, so this should have been 100. Okay, let's do that here. 100. Let's make this 333. I'll stop doing things in my head. All right, so make sure you got those corrected in your notes. 3 times VC should be 0.100. We do divide both sides by 3, and then that's going to give me 0.0333 liters. If you have this on a test and you stop here, this is fine. I've just said, what is the volume? You found the volume. If you're in the lab, you might have to figure out how to measure out 0.333 liters. And we don't have any devices that divide a liter into decimals. We have milliliters. So you would have to convert that to milliliters. So there are 1,000 milliliters times 1 liter. And that would give you 33.3 milliliters. Okay, so what did I do on Friday? On Friday, I left everything in milliliters and I didn't convert to liters, but I still got to the right answer. So let's see what we would do here. Let's go back up here and leave out this conversion. So 3.00 moles per liter times VC is equal to 0.200 moles per liter times 500 moles. The moles per liter here and here can cancel each other out. Those units will cancel. So if I go ahead and move that number over, I would have the volume, the concentrated volume that I need is 0.200 moles per liter times 500 milliliters divided by 3 moles per liter. Those cancel, and I'm left with units of milliliters. So if I plug this into my calculator, 0.2 times 500 divided by 3, I get 33.3 milliliters. Okay, so I get to the same answer. I was looking for concentration last time rather than volume, but essentially what happens is I converted this to liters by dividing by 1,000, and then I converted this back to milliliters by multiplying by 1,000, and those two things canceled each other out. So that's why it worked out to the same number on Friday. That makes sense. Okay, the last section of your book talks about some other forms of concentration. So I'm just briefly going to talk about section 4 in chapter 3.